Hello, everyone. We're working through an introduction to statistical methods and data analysis by Ott and Longnecker. Chapter 14, Part 1, Anova for completely randomized designs. So just as a reminder, in a completely randomized design, we have our experimental units, and we are separating them into T different treatments, and then comparing those T treatments using an overall F test and doing an Anova table. So we're going to do an example here. Researchers from the Department of Fruit Crops at a university compared 4 different groups of preservatives to be used in freezing strawberries. The researchers prepared the yield from a strawberry patch for freezing and randomly divided it into 4 equal groups. Within each group, they treated the strawberries with the appropriate preservative and packaged them into 8 small plastic bags for freezing at 0 degrees Celsius. The bags in group 1 served as a control group, while those in groups 2, 3, and 4 were assigned 1 of 3 newly developed preservatives. After all 32 bags of strawberries were prepared, they were stored at 0 degrees Celsius for a period of 6 months. At the end of this time, the contents of each bag were allowed to thaw and then rated on a scale of 1 to 10 points for discoloration. Low score indicates little discoloration. The ratings are given here. So in this case, each of those bags of strawberries indicate an experimental unit. They were assigned to 1 of 4 groups, where group 1 is the control group and 2, 3, and 4 are the different preservatives. And at the end, we see the ratings. So our YIJ in this case is the ratings of discoloration, and the groups are the treatments. So the different type of preservatives are the treatments. I'm going to put this data into R to be able to analyze it. So first I assigned a variable called group, and that gave me a value of 1 repeated 8 times for each of those bags, and then a value of 2 8 times, 3, and 4. I put in the YIJs by inputting the data directly. I created a data frame by using the as.dataFrame function. And the cbind function is saying bind these together in columns. So column 1 is going to be group, and column 2 is going to be YIJ. And then I am binding those in columns, and then I'm creating a data frame from there. By doing summary of data, I can see the summary, which gives the 5-number summary as well as the mean. Okay, so for groups, the minimum group number was 1 and the maximum group number was 4. All right, for the YIJs, the minimum value, the lowest discoloration was a 1 and the highest discoloration rating was a 10. Using the table function for data $ group, I see that there's 8 bags in each group, and that was just a spot check to make sure that everything is looking good. I create a new variable called fit.cr using the LM function, and remember the LM function stands for linear model. And I'm regressing the response on the factor of a group. So the reason I'm using the word factor here is because right now R is only recognizing group as a number, since I just gave it 1, 2, 3, 4. But I'm just telling R, hey, by the way, this isn't really a number, these are groupings. So create this factor for my linear model. I tell it the data set, which I have saved as data here. If you had a different name for your data, you would say data equals my strawberry data, right? Whatever you called it. Okay, summary of fit.cr gives you the summary of the linear regression model. Here's your coefficients, right? So this is if I wanted to estimate each of those coefficients. The way we would look at this, we would have your y hat would be equal to 8.3125 minus 1.875 group 2 minus 4.3125 group 3, right? Minus 5.8125 group 4. Now, essentially, group 2 is either going to equal 0 or 1, right? That's just an indicator function. If you're in group 2, set it equal to 1. If you're not in group 2, set it equal to 0. When group 2, group 3, and group 4 are all 0, that means you're in group 1, right? So the average rating for group 1 is estimated, the sample average is 8.3125. For group 2, it's going to be 8.3125 minus 1.875. For group 3, it would be 8.3125 minus 4.3125. And for group 4, it would be 8.3125 minus 5.8125. All right, you get your adjusted R squared value, but you also obtain your F statistic right here. Remember, if everything was equal and the regression mean square was the same as the mean squared error, this F value would be 1, right? The F distribution under the null hypothesis peaks at 1, right? We get a value that's very, 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 very large, right? Our F test statistic is 55.67, and we get this area right here, which is approximately equal to 0, right? It's less than 0.001. Okay. We can obtain the Anova table by taking Anova of fit.cr. I just called it fit.cr because fit.completely randomized design. You can call your fit whatever you would like, but we can set this up. So we had 4 treatments. So our degrees of freedom for the treatment will be 3, right? We have a total of 8 times 4, 32 is our sample size, right? N equals 32. T equals 4. So our total degrees of freedom here, the residual degrees of freedom here should be 32 minus 4 is 28. Our total degrees of freedom is just n minus 1. So 32 minus 1 should give us 31. And if we spot check 28 plus 3, yes, it equals 31. All right, our sum of squares is 159.187. Our sum of squared error is 26.687. Now, if you want to hard code this by hand using the formulas from earlier in the chapter, you're more than welcome to. But when you're working at a job and in the real world, I doubt you're ever going to code these formulas by hand. Your mean square for treatment is just your sum of squares treatment divided by the degrees of freedom. So you can verify that the mean square is 53.062. And the mean squared error, same thing, sum of squares error divided by the degrees of freedom of the error term, that's 0.953. Okay, so essentially that ratio of the mean squares becomes our F value, and we get a value of 55.672, and our p-value is less than 0.001. Okay, so if we're testing if there's a difference in the mean ratings, we're really saying HO, does mu1 equal mu2 equal mu3 equal mu4? And HA, right, at least one of the mu i's does not equal the rest, okay? And just by looking at a box plot, we can see that there's quite a difference between the different preservative groups, right? Group 1, this is your control. And then this is preservative 2, preservative 3, preservative 4, right? So these groups definitely look different just by plotting the values themselves. But by taking the F test, that overall F test, we see, yes, what I'm seeing, they look different, but mathematically, when I do this calculation, they are definitely like significantly different from one another. At least one is significantly different than the rest. So you would say that the type of preservative does change the amount of discoloration. So for example, I wouldn't necessarily want to use preservative 4. Wait, let's look at this real quick. Let's rephrase. I would want to use preservative 4 because that results in the least amount of discoloration, right? Because even if you know that the strawberries are fine to eat, if you open a bag of strawberries and they're very discolored, they're not going to look very appetizing. So you might end up wanting to have a preservative with very little discoloration. All right. If we want, you can see on page 9 of our notes, this is very similar code to what I just did. But the thing that I'm showing you here is if you had created different variable names, so you could have said data $ discoloration gets data $wij, and you could have said data $group with a capital G now gets factor of data $group. Right? Then your code could be adjusted here to get the fit, but you're still getting the same exact values. You can get an Anova, you can create a box plot. So that's just a slightly different set of code. Either set works, it just gives you some alternatives. All right, I hope you learned something in this video, and I'll see you next time.